All right. So we're going to look at molecular orbitals for more difficult molecules.
Yay.
Did we? I don't think we did BH3.
I think we did. We did.
Did we?
Yeah.
Oh, so okay. So we start like we were just looking at the molecular the orbitals on boron. Okay, so we saw that the PZ orbital is an A2 double prime, and the PX, PY are E primes. Okay, so we did that. Let's start looking at the ligand group orbitals. We're going to look at this from the top down. So what we're going to have so again, they're hydrogens. So they're just going to So it's just going to be a nice little triangle here with our rotation axis at the center. So we're just looking straight down on the top of it. And so what we're going to do is we're going to call these one, two, and three. Okay, so what we want, the first thing we want is so we want the representation for our unchanged orbitals, okay, within the symmetries of our D3H. Okay, so our first symmetry, E, how many of those are unchanged by E?
All of them.
Yep, so it's 3 of them. C3, how many are changed by that?
None of them.
So yeah, none of them stay the same. So let's think about the C2s. How many stay unchanged if you perform a C2?
Just the one.
Yeah, just the one. Because of course your C2 going to be right down the middle there. So you have, we can just say like side 2, side 3. That'll flip, but side 1 will stay the same. Okay, what about sigma H?
3 of them.
3 of them. All right. And what about our S3?
0.
0. Because you have to have that C3 rotation first. What about the sigma V's?
Also 1.
1. Okay, now, this is helpful because when we looked at the orbitals for boron, we saw we had an A2 double prime and an E prime. Now, what we noticed is if we add together the A2 double prime and the E prime from the table there, oh, sorry, I forgot one. So your 2s for your boron is A1 prime. We talked about that as well, didn't we?
Yeah.
Yeah, okay. So we have the A1 prime, the A2 double prime for the 2PZ, and the E prime for the PX and the PY. Now, what you're going to notice is which 2 rows from the character table, when you add these together, will give this representation for unchanged wave functions. Now we know we can't use E double prime because one of our boron orbitals is an E prime. So we're limited to A2 double prime, E prime, and A1 prime.
I would say E prime and A1 prime.
Yep, that's right. When we add together the A1 prime and the E prime, we get this representation. So we know that our ligand group orbitals have to follow the A1 prime or the E prime. So the That means our A2 double prime, our PZ orbital is going to become what? What's that going to become again?
The PZ.
Yep. It has a different symmetry than the ligand groups that are available, and the 2s and the px and py from the boron.
Oh, it's a non-bonding?
Non-bonding. So that'll come out as a non-bonding orbital.
Okay.
Because again, symmetry-wise, it's not going to be able to match with anything. Now, we want to start getting an idea of what these wave functions look like. So let's ask ourselves a question. I'm going to like take this. Yeah, maybe I'll just move it down because I need to get some stuff in here. And let's put it here. Okay, because what I want to start drawing in is, okay, so we have the C3. Let's do, okay, so each one of these we'll get a C2. Then let's draw in. So these, what we have, so we're going through sigma V1, going through psi 1. Sigma V2, sigma V3. Then we know that our sigma H we'll have to draw on here. All three of those lie right in the plane of the sigma H, so we can look right down on it. And then of course, our S3 is going to use the C3 and the sigma H. Yes, that's really all we need. Okay, so let's start looking at what happens to psi 1 as we use each one of these. So for E, psi 1 stays psi 1. For C3, let's see, so for C3, psi 1 becomes I know I have the C3 drawn that way. Let's, just to make sure you can pair this up with the book, let's rotate that way. We could do this rotating any direction, but I want to make sure you can check this with what's in the textbook. Okay. So in this case, psi 1 rotates into what?
Into psi 2.
Psi 2. Okay, what about your C3 2?
Into the psi 3.
Yep, so psi 1 becomes psi 3. Okay, so C2 1, that's going to be the one going straight down psi 2. So then C2 2 goes through psi 2, and C2 3 goes through psi 3. So the one we have drawn there is the C2 1. What happens to psi 1 with that rotation?
It's psi 1 still.
Yep, stays psi 1. C2, the second C2.
That'll turn into psi 3.
And the third C2.
Go to psi. Wait. Yeah, I'll go to psi 2.
Psi 2. Okay, now our sigma H. Psi1 just stays Psi1. Okay. For our S3. So think about this one real carefully. S3, we have to do the C3 then the sigma H.
Okay, so that'll be psi 3.
Which way is the C3 rotating?
That way. Oh, so it's psi 2.
So these will match your your C3 rotations. So then your S32 is going to become psi.
Psi 3.
Oh,
Right.
like I wrote this down up here. That becomes 3. That becomes 3. And your sigma V1.
Sigma V1. Which one? Okay, that will stay as psi 1.
Sigma V2.
Will it be psi 3?
And sigma V3.
Psi 2.
So what we have here is when we add all these together, the size for this ligand group orbital can be, so we're just looking at these in order. And when we add all these up, what we're going to get and so we're going to pull those fours out front. And so the book gives normalization constants, but we're not real worried about that right now. What you're going to be getting is a normalization constant. And looking at this, which symmetry would you say this is going to go with?
Which symmetry would I say this is going to go with? Is it just going to be E?
Nope.
No.
See how I have a symmetric contribution from psi 1, psi 2, psi 3?
Right.
This is the completely symmetric representation, which if we go back up is what?
Symmetric represent. Oh, A1 prime.
A1 prime.
Oh.
So this ligand group orbital right here that we see at the very top left, that is our A1 prime representation. Okay, let's think about the E prime. Okay, so E prime is going to have two symmetric representations. It's going to have to be represented by nodes that are perpendicular to each other. Okay, so I don't know, let's look at the first one. Did I put in here why they made that one bigger? Oh, yeah, there's a reason. Okay, so what we're going to be looking at, we're going to have the larger node on top. So keep in mind, I'm drawing this preemptively before I know the wave function. All right, and then so the first thing we're going to have to calculate is this with a with a node this way. And so then if we look, so if you go through that whole process again, what you're going to end up with no, actually, let's see if we can, I'll give you the second one. Let's see if we can come up with this one. Okay, so again, you have all the same symmetry operations. So your E, sine 1 stays sine 1. For your C3, now this is where you say, so sine 1 becomes a negative sine 2. Do you see that? It's the opposite phase.
I see.
So C2, 3, negative sine 3. Let's see. C2, sine 1. C2, 2, negative sine 3. C2, 3, negative sine 2. Sigma H, sine 1. S3. It's going to be a negative sine 2. S2, 3. Negative sine 3. I'm hoping this comes out right because I didn't do this last time. I just want to see how it works. Let's see if I'm missing something. Sigma V1. Sigma V2. Sigma V3. I'm seeing enough of these side 3s and side 2s that I'm thinking something may have happened. We'll figure it out. Yep. What do we get? Yeah, so see, we're coming up with 4 of those again. Well, something happened. I'll have to work this out in my spare time and figure out what happened.
What?
Need to go back through and look at these rotations again, see if I can't figure out why that did that. Yeah, I'll show you the way it's supposed to come out, and I'll figure out what happened. So what you're supposed to get, so your first E prime, you get your normalization constant, and you end up with 2 psi 1 minus psi 2. So I'll work back through and figure out where that went awry, but that's why that one on the top is bigger. Because you get double the representation from it. Then what we're going to want is we're going to want a node that goes like this. Okay, so what you end up with is you end up with an orbital situation where this s orbital at the top is not going to contribute. So it's only going to be those two down at the bottom, and you end up with your second E prime. That bugged me. I know I had it worked out last night. I just didn't write it down. So this is going to be your second E prime contribution. Okay. So now we want to start thinking about how these come together. We're going to let orbitals with the same symmetry interact with each other. So this, I'm going to redo this and actually come up again with what I had last night and be like, oh, okay, that's how it works.
All right.
Okay. So orbitals with the same symmetry are going to, so our A1 prime for our boron is our 2s, and our E prime pair for boron is our 2px or 2py. So let's start putting these together. What do you think a good A1 contribution is? So let's go back up to your A1 here. How do you think this, what do you think this will look like?
I bet it'll kind of just be like evenly distributed throughout the molecule.
Yeah, so you imagine boron in the center.
Yeah.
You're going to have, let's go ahead and draw the ligand group. Okay, and then in the center, you get this boron 2s. This will be our A1 prime representation. Now, let's think about one of our E1 prime contributions. So what is a bond? Let's see, what is a bonding contribution? I'm just going to call these, because we're looking straight down on it, I'm just going to call each one of these 2p. Because I haven't set an X and Y axis. So let's look at this this first E1 prime ligand orbital. That's good. Now, how do you think the p orbital would fit in here to cause bonding?
I mean, are you gonna have like two of one phase going kind of like that, and then two of the other phase going kind of?
No, we're just looking for just one of the p orbitals right now.
Just one of the p orbitals. Okay.
Because the other one will interact with the other E prime representation.
So I think it'll do the one like head on.
Yeah.
And then it'll kind of be like sideways with, yeah.
And so this is going to give you your first E prime representation. And then, so we want this second E prime representation. Did I write that down wrong? Yes, I did. Of course I did. There we go. That's the correct second ligand orbital.
Okay.
Because the way I had it, it was perfectly symmetric again.
Yeah, but one of them is positive.
Yep.
I could. I can understand.
All right, so let's look at this one. So of course, we just put that little dot where the other boron or the hydrogen 2s orbital would be that's not contributing. And then we think that so then we say that our second p orbital will do something like this. So that's a 2p, that's a 2p. Again, you could label either one of these X or Y. And then, of course, we remember we're going to have this boron 2pz orbital. Okay, so this is your E prime. That's your second one. And then this one is your A2 double prime. That's your non-bonding orbital. Okay, now let's look at these again. We have to put together the same symmetries, but we need antibonding. So let's just go ahead. I'm just going ahead and grab this. How do we think antibonding is going to shape up?
I mean, maybe the boron one is in a different phase.
Yeah. So we just okay, and then grab both of these E primes. So let's make sure we got this right. This is our A1 prime star. That's our antibonding. And then here, it'll realign that way. And this will be your first E1 prime star. And then we'll grab this other one. So I'll just reverse that. And we get our second E1 prime star. So now we have our antibonding orbitals. Okay. Now, okay, this one I went along with the textbook. I'm going to make an argument the other way for methane. So let's build the molecular orbital tree.
Okay.
So we go back up here. So which one is the lowest energy?
A1 prime.
A1 prime. And then the E2, the E primes, those two, what would those look like? So I could say I'm going to put an A1 prime there. How would I do the E prime level?
I mean, I think they'd be pretty much the same. Would they be next to each other?
Yeah, they're the same energy.
Yeah.
Mm-hmm.
Cool.
That'll be fun. What that's going to be. That's our E. Oh, okay. That's just. Oh, we're getting all kinds of things messed up. These are not E1s. These are just E's.
Just E.
Again, just go back. If you just go back up and look at the character table, that's what we're limited to. Okay, then we're going to have our non-bonding level. So it's just going to kind of sit right here in the middle. Then we're going to have our A1 prime star. And then our E prime star. Okay, so that is the molecular orbital structure. So then we stay over here on the right side. So our boron is going to have to give us a 2s orbital. It's going to be just a little bit up here. And then our p orbitals here, we're going to align these so that, okay. So this would be, this top one would be our 2pz, A2 double prime. These other two are 2px, 2py, and these are our e primes. This one down here is our 2s. That's our A1 prime. Then over on the other side, how many orbitals do you think we'll have over there?
Will there be 3?
3, because that's going to account for the ligand groups.
And they'll be like way down.
Kind of. So they're going to be kind of between these two. So here's your E primes and your A1 prime. So then we have to draw out our structure. Okay, so A2 double prime. We can go straight across to A2 double prime. Your E primes. Your A1's got to connect to A1's. And so this is what our structure would look. Well, this is the one that matches the textbook. I kind of disagree with it. I'll make that argument with methane because according to the quantum mechanical calculations, the E prime star and the A prime star should be flipped, should be switched. Because when you calculate them, the A prime star is a higher energy than the E prime star. So I decided, because once again, the textbook disagreed with me on methane as well. And I think that the textbook is just doing these in order: A1 prime, E prime, A1 prime, E prime, all the way up. But I want to start representing these in the energetic order that they come out in. So if you wanted this in the order that the quantum mechanical calculations give you, you're going to flip the E star and the A star. Now let's see if you can pick these out. So here are the orbitals we calculated.
Okay. That one's got to be A1 prime.
Mm-hmm.
That one's gotta be the E prime, the first one.
Yep, so that's one of your, so this one, if we think about it, so yeah, this is,
Oh, no, that's E prime two.
yeah, this is E prime two.
Okay.
Because if you remember, that's gonna be. Your node center. And then what, you have your. So that's gonna be that one.
That one's gotta be E prime one.
Yep, that one's E prime one.
And then that one's your two PC. The A2 double prime, I guess.
Mhm. Let's think about how this one's made, so we can kind of get an idea. You seem to feel more comfortable with these today.
I think so. I think so. I'm understanding.
That's gonna be that one. Uh-oh.
Okay. That's gonna be A1 prime star.
Mhm. So of course, that one is, you have your different phase in the middle. I'm just gonna copy this from here. So. That's that one.
That's gonna be E prime star one. Right?
Let's see here.
Yeah, because that one doesn't have the
Yeah, it is. Okay, so. Go, because again, you can see that orbital. If we rotated this, you can see that orbital up on the top. And then you can see that kind of P, or that what's left of that P orbital, the antibond, the different phase sticking out the bottom with those two ligand group orbitals down at the bottom, kind of connecting slightly through the center. Kind of doing something like this.
Yeah.
And then, of course, our last one.
Yeah.
We'll grab it. You already said what it was.
Yeah, that's the second E prime star.
Yep.
Yeah.
So then we look at it again and we say, well, there's our tree with each one of them in place. Again, the quantum mechanical calculation actually flips the A star and the E star. And so I just decided, well, I'm going to go ahead and start doing that too, because I'm going to go with what the computational programs are telling us. Let's see if we can make it a bit harder. So methane, we're actually going to use cubes for this because we get a cubical symmetry. Tetrahedral symmetry, but it fits with inside a cube. Okay, so this is the TD point group. Let's think about what the carbon has to offer. Not really going to worry about the three-dimensional drawing. Okay, so there is going to be a 2s orbital. And what symmetry do you think that'll have?
That'll be A1.
That'll be your A1. Okay, now let's see how you handle this one. Because I could rotate this any direction and have any hydrogen facing up and get the same structure. Okay, so Okay, so, all right. Go ahead and draw that one coming out. Going that way. It's back there. We have PX, PY, PZ all together here. So look at that character table. Seeing as how I could rotate this any direction and get these same orbitals going, you know, these are all going to be together. So it has to be one of two of those representations. Which ones do you think? How many
T2.
Yeah, it is T2.
Really?
Yeah. Fine. Okay, fine. What does T mean?
I don't know.
I was kind of going towards that, but you're like,
I guess.
but you're like, yeah, T2, hell with it. So yes, this is the T2 representation. So how many degeneracies does E have?
How many degeneracies?
Mhm.
So it'll be the 3 because there's the 3 orbitals.
Well, no, look at the E. So when we've been doing E, how many orbitals is that? How many degenerate orbitals? We just did an E. How many degeneracies did it have? How many dimensions does it have there on the table?
It's got 3.
The E.
The E?
Yeah.
Okay, just 1. What do I know what I'm talking about?
So let's go back up. Look at the E. How many degenerate orbitals does it have?
How many degenerate orbitals does the E have? 2?
2.
Oh.
So that's a twofold degeneracy. The T, that's your tertiary degeneracy, which means it has how many degeneracies?
3.
3. So your tertiary is a threefold degeneracy, and you see your PX, PY, PZ all there together.
Okay.
But then you could say, I was hoping you would say it's one of the T's, and then you could say as you rotate this through some of these operators, you're going to get that. You're going to get that -1, and your sigma D's will be a 1, and that tells you that it has to be the T2. But since you're really good at guessing,
Yeah.
Okay, so that's your T2 symmetry.
Okay, I can see it. I think.
Go back through and look at some of the symmetry operations for methane. Now, the reason we're going to be using cubes, let's start thinking about these ligand group orbitals. Okay. All righty. So I'm gonna kind of tip it on its side. Because you remember another way to write this is do you remember we can also do this? Okay, so that means we have an orbital there. We have one there. One on that corner. And one on that corner. If you think about it, let's just say we had our carbon right at the center of this. You can actually see the tetrahedral fit right inside that cube.
Yeah.
Okay, so the way we're going to label these, I went counterclockwise for this one, but okay, and then I want to mark which axis is that?
That's going to be a C3.
C3. Okay, so then that means, so that tells us that coming straight up here through the middle, what's that?
That's a C2.
C2. Some of these are easier to see when it's tipped on its side like this. All right, so let's. Our gamma for our unchanged. Okay, so for E, how many of those stay unchanged?
Oh,
So 4. For your C3, how many?
just one.
1. All of your C2s. So let's look again. So I have 3 of those. C2,
None.
none of them stay the same. S4.
It's four.
So S4, what it would do is like you see it takes Psi1, it move it to that corner and then reflect it down.
So none of them.
Yeah, so none of them. And sigma D's. So here's a way we can think of a sigma D. This is another reason I like the cube. So if I went like this, on the corner like that, this plane is a sigma D.
Oh, okay.
So how many stay unchanged?
2.
2.
Okay.
Yep. So that's how the sigma D's work. But okay, so now we could go ahead and say, well, we already know the symmetries of the orbitals are A1 and T2. So if I combine A1 and T2, I should be able to get this. But let's start actually. Working through the size of this. Now I know what I wanted to represent there. I'm missing like a whole page. Let's see, we have those. We have those. All right, well. This kind of showed up here. Now, let's start going through. For my E, Psi1 stays Psi1. Oh, wow, we are out of time. Aren't we?
Oh,
Okay,
all right.
we'll pick this up again on Friday.
It was next Friday that you're not gonna be here. Also, do we have a quiz this week?